Come on, my dears, let us proceed further in chapter number 6. Kindly read this statement of illustration number 2. Come on, have you read it? Look, we are given one nucleus, visually 26, ferrous 56. In the first question in this example, we are asked to find out binding energy per one nucleon for this nucleus. Let us find out. See, first of all, whichever nucleus is given to you, you should compare it with ZXA, correct? Then you will get here Z equals to 26. And what about capital N? Formula of neutron number is A minus Z. N equals to A minus Z. So it is this minus this. So it is this minus this. 56 minus 26, it is 30, correct? So in the nucleus of ferrous, there are 26 protons and 13 neutrons, correct? For finding binding energy, remember, first you must find out mass defect. What is mass defect formula? Delta M equals to ZMP plus NMN minus capital M. What about Z? Right now it is 26. What is MP? Mass of one proton in a free state, which you are given in the statement 1.007825 atomic mass unit. Capital N is number of neutrons, which is at present 30, multiplied by Mn means mass of one neutron in a free state, which you are given in the statement as 1.008665 atomic mass unit, minus this is mass of a given stable nucleus. Mass of this stable nucleus you are given in the statement 55.934939 atomic mass unit, correct? 55.934939 atomic mass unit. Now all these values of masses are also in atomic mass unit. This is also in atomic mass unit. So the subtraction you will get in atomic mass unit, and exactly you will find the answer 0.528461 atomic mass unit. Now tell me, in the statement you are given that one atomic mass unit is equivalent to 931.494 million electron volts of energy. That is what they have given. And now we know one thing, binding energy is energy equivalent to mass defect. Energy equivalent to mass defect. So you should find out energy equivalent to this many atomic mass unit. What is the energy equivalent to one atomic mass unit? It is this many million electron volt. Then energy equivalent to this much mass in atomic mass unit would be equal to this into this. That's what I written here, 0.528461 multiplied by 931.494 million electron volt. This multiplication comes out to be 492.258 million electron volt, correct? Fine. And now tell me, what is asked to us? Binding energy per one nucleon. It is shown by symbol EBN, correct? And it is nothing but total binding energy divided by total number of nucleons. But total number of nucleons means what? Atomic mass number, that is capital A. So you should divide EB by capital A. What is EB value? 492.258 divided by A. What is the atomic mass number right now? It is 56. So A is 56, correct? And now this upon this, answer is 8.79 million electron volt per nucleon. What do you mean by binding energy per one nucleon? Binding energy per one nucleon. What is the meaning from physics point of view? I am showing you. See, inside the nucleus, all the nucleons are bound together mutually, correct? If you want to make them freed completely from the mutual binding, then you are supposed to give energy to each nucleon. When we want to make all the nucleons freed from mutual binding, at that time whatever energy we require to supply minimum to one nucleon, that minimum amount of energy is only known as binding energy per one nucleon. I repeat, when we want to make all the nucleons freed from their mutual binding, at that time whatever minimum amount of energy we have to supply to one nucleon, it is called binding energy per one nucleon, correct? Fine. Now tell me, in the second part of this same example, they have asked one more question. Let us find out its answer also. We are given this nucleus, which one? 26 ferrous 56. And what does it do? It simply makes, it just liberates one proton, which is most loosely bound, okay? Most loosely bound proton is liberated from this nucleus. Let us write this reaction, correct? Come on, this is the given nucleus. It simply generates, it simply emits what? One proton, which is most loosely bound. Let me tell you, proton is nothing but nucleus of hydrogen. Proton is nothing but nucleus of hydrogen. So I am writing here hydrogen, that is 1H1, which is nothing but proton only. When this emits one proton, tell me, balance the reaction. 26 minus 1, it is 25. And with atomic number 25, what is the element in the periodic table? It is manganese. It is manganese, shown by symbol capital M small n, you know from chemistry. Then 56 minus 1, that is 55. So as this nucleus emits one proton, which is most loosely bound, it so happens that it gets converted into this nucleus 25, manganese 55. Now let us compare final and initial masses. Let us compare. Let us find out final mass. Final mass means mass of this plus mass of this. Mass of this manganese nucleus plus mass of proton. Okay, let us find out. Mass of this manganese nucleus you are given in the statement 54.938046 atomic mass unit. Mass of one proton in a free state you are given in the statement 1.007825 atomic mass unit. And this summation comes out to be 55.945871 atomic mass unit. Now tell me, what is the mass of this ferrous nucleus? You are given in the statement. Mass of ferrous nucleus is 55.934939 atomic mass unit. Can't you see? This mass, which is final mass, is greater than this initial mass. If final mass is greater than initial mass, what does it indicate? That in this reaction, mass is increasing. Mass is increasing. See, as such, mass will not increase. As such, mass will not increase on its own. So this process will not take place on its own. This process can't happen on its own. No, it can't happen, because there is some increase in the mass. So now if we want that process should take place, if we want that process to happen, then we need to supply some energy from outside. In the input, we must supply some external energy, and your energy supplied will get converted into equivalent mass, and that's why mass is increasing. So this process, if we want to make it happen, we must supply energy. But once you supply that energy with the minimum value, it so happens that most loosely bound proton is getting emitted, correct? So, whatever energy you are supplying, that must be binding energy for that liberated proton, because unless you supply that energy, that proton remains very much bound, and as soon as you supply that energy, it gets freed. So, that supplied energy gives you binding energy of that proton, which is most loosely bound. Okay. Let us find out now binding energy of that liberated proton. It is nothing but energy which we have supplied. But whatever energy we have supplied is ultimately converted into increase in mass. So, we should find out energy equivalent to increase in mass. Energy equivalent to increase in mass. So, first of all, let us find out increase in mass. Increase in mass means what? Bigger mass minus smaller mass. Bigger mass is this, smaller mass is this. Let me subtract smaller mass from bigger mass, and that increase in mass I should multiply it by 931.494, this many million electron volt, because I know given in the statement that one atomic mass unit is equivalent to this many million electron volts of energy, then this much is the increase in mass in atomic mass unit. It is equivalent to what amount of energy? For that I should multiply this subtraction with this number, which is 931.494 million electron volt. And now this minus this, answer is 0.010932 atomic mass unit multiplied by 931.494 million electron volts of energy, and this multiplication comes out to be 10.18 million electron volt. 10.18 million electron volt. Got it? Fine. Once again, let me remind you the meaning of binding energy per one nucleon. When all the nucleons in a nucleus are to be made free from their mutual binding, at that time amount of energy required to supply to one nucleon is called binding energy per one nucleon. Correct? Fine. Now, what is called separation energy? What is called separation energy? Fine. See, remember we had defined earlier about work function of a given metal in semester 3. Minimum amount of energy required to emit one electron from a given metal is called its work function. Similarly, this separation energy is minimum energy required for liberating one nucleon from a nucleus is called separation energy. Minimum energy required to liberate one nucleon from a nucleus is called, come on, separation energy. What is it called? Separation energy. Okay, fine. Look. Now we understand the another very important article about natural radioactivity. This is a very important phenomenon. Actually, history says that in 1895, Mr. Ronjan had discovered X-rays. Okay, fine. That's what I have written here. In the year 1895, Mr. Ronjan had discovered X-rays. But then 1 year later, in the year 1896, there was a scientist with name Mr. Henry Becquerel, and he was trying to study the relationship of production of X-rays with fluorescence. And at that time, accidentally, he came to know that heavy element like uranium, just emits out of it some invisible powerful radiations having some specific properties. This very phenomenon is known as, this very property is known as natural radioactivity, and any element having this property is called natural radioactive element. Property is called natural radioactivity, and the element itself is called natural radioactive element. Fine. those radiations which were emitted out of uranium were found to be of three different types. Let us give them symbols: alpha, beta, gamma. Okay. Initially, these radiations were known as Becquerel radiations because Mr. Becquerel had discovered them. Correct? So initially they were called Becquerel rays, but now we call them radioactive radiations. Radioactive radiations. Okay, fine. Now tell me, then after the discovery of this phenomenon, after that, majority research work was later carried by two more scientists, Madame Curie and Pierre Curie. Madame Curie and Pierre Curie. Pierre Curie happened to be husband of Madame Curie. Okay, this scientist couple had separated two radioactive elements from the ore of uranium known as pitch blende. There was an ore of uranium with name pitch blende, and from this ore they had separated two radioactive elements, and they were named as radium and polonium. Name of one element was radium, another name was polonium. Correct? Name of another element was polonium. So these two radioactive elements were discovered by Madame Curie and her husband Pierre Curie. Okay, from which ore of uranium known as pitch blende. Okay, fine. Now, as I said, the Becquerel rays, initially they were called Becquerel rays, but later on they became famous with this name, radioactive radiations. And any substance, any element having this property of natural radioactivity is called natural radioactive element. Let us see some of the examples of natural radioactive elements. They are uranium, barium, radium, polonium, actinium, thorium, thulium, bismuth, protactinium, plutonium, etc. These all are having their atomic mass number greater than 206. They are found to be naturally radioactive. Fine. Now tell me, what are the noteworthy points regarding the emission of these radiations? There are 3 points you must remember. First point, look, the emission of these radiations, we find it is self-inspired. No other external agency is responsible for that. It is a self process. Okay, fine. So it is taking place on oneself. It is a process which is spontaneous, and the emission of radiation takes place continuously. So process of emission of radioactive radiations is, come on, it is self also, it is, come on, spontaneous also, and it is continuous also. Fine. The second fact is this: there is no effect of external factors like pressure, temperature, electric field, magnetic field on the rate of emission of radioactive radiations. Come on, which are the factors? Look, which are the factors? Come on, pressure, temperature, electric field, magnetic field. Such external factors, they can't produce any effect on the rate of emission of radioactive radiations. Whether you increase pressure or you decrease pressure, whether you increase or decrease temperature, whether you apply electric field or not, whether you apply magnetic field or not, irrespective of any external factor, the rate of emission of radioactive radiations remain invariant. Okay, fine. And third, see here we can say, if no external factor can produce any effect on rate of emission of radioactive radiations, we must say that these are the radiations which are emitted from the nucleus. Because these radiations are emitted from nucleus, that is why there is no effect of any external factor. Now tell me, if radioactive radiations are emitted from nuclei, we can give another name to this phenomenon, which is nothing but nuclear phenomenon. So remember, natural radioactivity is also called nuclear phenomenon because radioactive radiations are found to be emitted from nuclei of atoms of radioactive elements. Because they are emitted from nuclei, we give another name to natural radioactivity as nuclear phenomenon. Got it? Fine. And last point, even if you associate a given radioactive element with any other substance chemically when you make combination, then also that combination does not affect the rate of emission of radioactive radiations. Okay. So these are the noteworthy points regarding the natural radioactivity and radioactive radiations. Okay. If you want to combine all these points and you want to give long definition of natural radioactivity, it is not there in the textbook, just for your kind knowledge. All heavy and unstable elements available in nature having atomic mass number greater than 206 emit out of them certain specific invisible powerful radiations on the rate of emission of which there is no effect of temperature, pressure, chemical mixing, electric field and magnetic field. Such a nuclear phenomenon is called natural radioactivity. I repeat, certain heavy and unstable elements available in nature having atomic mass number greater than 206 emit out of them some powerful invisible radiations spontaneously on the rate of emission of which there is no effect of any external factor like chemical mixing, electric field, magnetic field, pressure, temperature. Such a nuclear phenomenon is called natural radioactivity. Correct? Fine. Now, what is the reason for emission of radioactive radiations? What is the reason? See, these all elements are naturally unstable. You know why they are unstable? They have energy much more than what they require to remain stable. Because they have got enormous amount of energy, much more than what is required to remain stable, their immediate tendency is to emit excess energy, and after emitting excess energy, they would like to attain a state of minimum energy and hence a state of maximum stability. With minimum energy, they can be maximum stable. And if they want to attain a state of maximum stability, then they have to throw out the excess energy. And they really emit that energy in the form of three powerful radiations, alpha, beta, gamma. Okay, fine. Now let us compare some of the properties of alpha, beta, gamma radiations. Let us make a nice table so that for you it will be very easy to write down in the examination. For examiner it will be very easy to check it. Okay, come on. Here I am writing all the details for alpha radiations. Here I am writing all the details for beta radiations and here for gamma radiations. The aspect of comparison I have written here. First aspect, come on, composition. Alpha radiations are made up of alpha particles. Alpha radiations are made up of alpha particles and each alpha particle is none but one helium nucleus. Fine. Beta radiations are made up of beta particles and each beta particle is nothing but one electron. Gamma radiations are nothing but electromagnetic waves. Simple. Second aspect of comparison, that is mass. Mass of one alpha particle is mass of helium nucleus. Mass of one beta particle is nothing but mass of one electron. And so far mass of electromagnetic waves is concerned, it is massless because it does not contain any materialistic particles. They are simply electromagnetic waves. They do not have any particles inside. They are totally massless. What about charge? Charge of one alpha particle means charge of one helium nucleus. Inside helium nucleus there are two protons, two neutrons, out of which two neutrons do not have any charge. So whatever is charge of two protons will become charge of one alpha particle, and it is plus 2e. Charge of two protons you can always write plus 2e. Charge of one beta particle is nothing but charge of one electron, which is minus e. And because these electromagnetic waves are massless, they have to be chargeless also. Don't write electrically neutral. You cannot write electrically neutral, because electrically neutral means whatever is amount of positive charge, same is amount of negative charge. But here there are no charges at all, neither positive nor negative. So better you write chargeless. What about penetration power? Out of given radiations, whichever radiation can travel longer straight distance in a given medium is said to be having higher penetration power. Practically we find that alpha radiations travel shortest distance in a given medium. That is why they have minimum penetration power. That's what I have written here, minimum, correct? Come on, or lowest, minimum or lowest. Here the penetration power is higher than this, so I am writing moderate, medium, moderate, and here penetration power is maximum, fine. If you take this lowest penetration power as 1 unit, suppose, then this is higher than that. Practically we find nearly 100 times than this. So 1 into 100, that is 100, and here penetration power is maximum, it is 100 times than this. So 100 into 100, 10,000. So this will give you relative measurement of penetration power of all these radioactive radiations, fine. Now we go for ionization power. See, whenever any radiation passes through a given medium, you know what happens? That radiation happens to collide with the constituent particles of that medium, and if the incident radiation is powerful, then it will knock the electrons out of the atoms which are coming in the way, and if electrons are lost by the neutral atoms, they will be transformed into positive ions, and whichever radiation can produce maximum number of positive ions in the unit length of a given medium is said to be having highest ionization power. Practically we find that alpha radiations produce maximum positive ions in the unit length of a given medium. That's why their ionization power is maximum, correct? Here it is less than that, so I am writing moderate. Here it is minimum, correct? Let us write down now values of relative ionization powers. If you take this maximum ionization power for alpha radiations as 10,000 units, suppose, then here it is found to be 100th part of this. So divide this value by 100, then you will get the answer 100. And here it is found to be minimum, it is still 100th part of this, 100 upon 100, that is 1. Simple? Fine. What about deflection? What about deflection of these radiations in the presence of electric and magnetic field? See, electric field can deflect which particle? Tell me, charged particle. And if there is a charged particle in motion in magnetic field, then it may deflect that charged particle. So for deflection of radiation, it must have charge. Tell me, alpha radiations have charge, so they can be deflected. Beta radiations also have charge, so they also can be deflected. But electromagnetic waves, gamma radiations, they are nothing but electromagnetic waves. They are completely chargeless, and because they do not have any charge, they cannot be deflected. Alpha and beta radiations having charge can be deflected by electric and magnetic field. But gamma radiations, because they are electromagnetic waves, because they are chargeless, cannot be deflected by electric and magnetic field. Fine. Now let us make note of other two very important points. First, all these radiations, alpha, beta, gamma, all of them produce effect on fluorescent screen. They also affect photographic plate. So there is some effect observed of all these radiations on fluorescent screen also, on photographic plate also. One more point. So far velocity of alpha and beta particles are concerned, they are found to be dependent on the type of radioactive element which emits them. But so far velocity of gamma ray is concerned, its velocity does not depend on the type of radioactive element which emits it. Okay. Velocity of alpha and beta particle depend on the type of radioactive element which emits them, but velocity of gamma ray does not depend on type of radioactive element which emits it. Okay, fine. Now after this, in textbook they have directly gone for activity of a radioactive element, but that article and then after the further part of the chapter you will not understand if you do not understand these two articles first. Previously in the old syllabus, these two articles were there in the chapter, these two articles were there. By mistake, those two articles have been skipped from the new textbook. But if you don't understand these two articles, you cannot understand further part of the chapter. So better you try to understand from here, please. What do you mean by radioactive disintegration? This word now onwards in the later part of the chapter they have used often and often in the textbook, but nowhere they have explained what is called radioactive disintegration. Better we should understand. Radioactive disintegration, what do you mean by that? It is a phenomenon. I am showing you which phenomenon. Consider a radioactive nucleus 84 polonium 210. I say this nucleus is artificially radioactive because, not artificially, I am mistaken, this nucleus is naturally radioactive. Come on, naturally radioactive, because you see atomic mass number, if it is greater than 206, the element will be naturally radioactive. And here the atomic mass number is 210, which is greater than 206. So this element is naturally radioactive. Fine. Now this natural radioactive nucleus is found to be emitting out of it alpha particles. So if it emits one alpha particle, then what will happen? I am showing you. Here I have written alpha particle, correct? What do you mean by alpha particle? One helium nucleus, symbol 2He4. Tell me what is the atomic number here? 84. What is here? 2. 84 minus 2, that is 82. With atomic number 82, what is the element in the periodic table? It is none but lead, Pb, lead, Lead, lead. Okay. And this is atomic mass number. How much? 210 minus 4, that is 206. Now tell me, what does this reaction indicate? It tells you that as soon as this radioactive nucleus emits one alpha particle, that nucleus no longer remains of polonium element, it simply transforms into a new element, and that new element is lead. Such a process of transformation from one element to another element, that process or that phenomenon itself is known as radioactive disintegration. Process whereby radioactive nucleus emits alpha or beta particle and gets transformed into nucleus of new element is called radioactive disintegration. I repeat, a process or phenomenon whereby a radioactive nucleus after emitting alpha or beta particle gets transformed into nucleus of new element is called radioactive disintegration. This nucleus which disintegrates is called parent nucleus. This nucleus which is newly formed after the disintegration process is over is called daughter nucleus. Correct? As I told you, majority research work was carried out by Madame Curie, and because Madame Curie she had favored daughter. Correct? She never said this is called son nucleus, this is called daughter nucleus. Okay, fine. Now tell me, this is parent nucleus, this is called daughter nucleus, not son nucleus. What is it called? Daughter nucleus. Fine. And this is emitted particle, right now it is alpha particle. Correct? Fine. Now this radioactive disintegration was studied experimentally by two scientists. One was Mr. Rutherford and another was Mr. Soddy. Mr. Rutherford and Mr. Soddy had studied this radioactive disintegration practically and had obtained some very important conclusions which are called laws of radioactive disintegrations. There are two, one is for alpha emission, another is for beta emission. I am showing you one by one. First, law of alpha emission. The same is law of alpha emission because here alpha particle is emitted. Tell me, how would you describe it in words? Very simple. Whenever any parent nucleus emits one alpha particle and gets transformed into daughter nucleus, comma, its atomic number decreases by 2 units and its atomic mass number decreases by 4 units. This very statement is called law of alpha emission for radioactive disintegration. I repeat. Whenever any parent nucleus emits one alpha particle and gets transformed into daughter nucleus, comma, its atomic number decreases by 2 units and its atomic mass number decreases by 4 units, full stop. This very statement is called law of alpha emission for radioactive disintegration. Simple. Now let us write in general. In general, how would you express that reaction? Very simple. Symbolically, ZXA, suppose this is parent nucleus. It emits what? One alpha particle, that is helium nucleus, 2He4. Here what is the atomic number? Z. What is it here? 2. Then here you must write Z minus 2. Fine. And as atomic number changes, the element would change. As element changes, you must change the chemical symbol also. From X, you must change it to Y. And here atomic mass number is A, here it is 4. So here you must write A minus 4. Correct? Fine. What is law of beta emission? Quite simple. We have another example, say 83 bismuth 210. What does it do? It emits one beta particle. Beta particle, that is electron, symbolically it is shown by such a symbol, minus 1 E0, minus 1 E0, fine. And tell me what is the atomic number here? 83. What is it here? Minus 1. So here you must write 84 because 84 minus 1 will make 83. But with atomic number 84, what is the element in the periodic table? Polonium. Here it is, 84 polonium. So you must write here polonium. And 210 minus 0, that is 210. So what have you noticed? As this parent nucleus emits one beta particle, what happens? Come on, atomic number increases by 1 unit and atomic mass number does not change. Just pick out the same thing in words, will become law of beta emission. Whenever any parent nucleus emits one beta particle and gets transformed into daughter nucleus, comma, its atomic number increases by 1 unit and its atomic mass number does not change, full stop. This very statement is called law of beta emission. Law of beta emission for radioactive disintegration. Fine. How would you express this reaction? In general, come on, symbolically ZXA, if this is parent nucleus and if it emits one beta particle, that is electron, minus 1 E0, then tell me here Z, here it is minus 1, so here I must write Z plus 1. Then only Z plus 1 minus 1 will become Z. And when atomic number changes, the element would change. And as element would change, you must change the chemical symbol. Instead of X, you must write Y. And A minus 0, that is A. Okay. Atomic number increases by 1 unit. Atomic mass number does not change. Regarding gamma emission, they had come to one conclusion. What is that conclusion? I am showing you. They noticed that whenever any element is naturally radioactive, say parent element, firstly it gets transformed into daughter element. Sometimes it so happens that even after coming into existence, the daughter nucleus is still unstable, excited. Then in the excited state, what does it do? It emits excess of energy in the form of gamma radiation, and then it gets transformed into ground state. Okay, it comes to ground state after emitting that excess energy. Now tell me, whenever gamma radiation is emitted, because it does not contain any materialistic particle, even after emission of gamma radiation, there won't be any change in atomic number or atomic mass number for daughter element. So atomic number and atomic mass number of daughter nucleus does not change though it emits gamma radiation. Then what does change? See, after emitting excess of energy, naturally the daughter nucleus will become more stable. So its stability would increase, correct? No change in atomic number, no change in atomic mass number, but after emission of gamma radiation, the stability of daughter nucleus would definitely increase, correct? Fine. Now, my dears, we take one very good definition about what is called activity or rate of disintegration of a given radioactive element. Let us define. Look. Activity or rate of disintegration of given quantity of given radioactive element at a given instant. Consider this as a time scale, okay, on which this particular instant I just take as t. This particular later instant I just take t plus delta t. So what is the time interval that has been lapsed between these two instants? It is this minus this, so it is delta t. Fine. Exactly at time t, the number of undisintegrated atoms in the given quantity of given radioactive element is suppose capital N. Fine. If number of undisintegrated atoms is capital N, meaning thereby you have capital N number of parent atoms, correct? Now you know, as the radioactive element disintegrates, it emits alpha and beta particle, gets transformed into daughter element, correct? So in this much time interval, suppose delta N number of parent atoms have been transformed into daughter atoms. Fine. What was the earlier number of parent atoms? That was capital N, out of which delta N have been transformed into daughter atoms. So what is the number of parent atoms, or what is the number of undisintegrated atoms at the end of this much time? It will be N minus delta N, N minus delta N, correct? Now in this circumstances, the rate of disintegration or activity is defined this way. I am showing you. Rate of disintegration is shown by symbol dN by dt, and the activity is shown by symbol I. Here we mean to say time rate of disintegration. What do we mean to say? Time rate of disintegration is shown by symbol dN by dt. It is also called activity, shown by symbol capital I. Now in the language of calculus, don't you know, dN upon dt means what? Yeah, limit delta t tends to 0, delta n upon delta t. Limit delta t tends to 0, delta n by delta t. Fine. Now the same term should be called now onwards as rate of disintegration or activity of given quantity of given radioactive element at a given instant of time. Right now that instant we have chosen instant t. Got it? Now how would you define it? Very simple. If delta n number of atoms disintegrate in time delta t after a given instant of time in a given quantity of given radioactive element, then the term limit delta t tends to 0, delta n upon delta t is called rate of disintegration or activity of that quantity of that element at that very instant. Full stop. I repeat, if delta n number of atoms disintegrate in time delta t after a given instant of time in a given quantity of given radioactive element, then the term limit delta t tends to 0, delta n by delta t is called time rate of disintegration or activity of that radioactive element for that quantity at that very instant of time. Full stop. This very definition is for activity or time rate of disintegration. Now I repeat for the last time. If delta n number of atoms disintegrate in time delta t after a given instant of time in the given quantity of given radioactive element, then the term limit delta t tends to 0, delta n by delta t is called rate of disintegration or activity of that quantity of that radioactive element at that very instant. Full stop. Got it? Fine. Now, this is no doubt rate of disintegration or activity, but at what time? At time t. At time t. Practically, we find that at any given time, the rate of disintegration is simply proportional to number of undisintegrated atoms at that very time. At time t, what is the number of undisintegrated atoms? It is n. Fine. If dn upon dt is proportional to n, you may remove sign of proportionality. You may put proportionality constant. Say here lambda I am putting. Don't change the symbol. Put lambda only. And without fail, you must put here negative sign. Why you have to put negative sign? Very simple reason is there. As time passes on, the number of undisintegrated atoms goes on decreasing. So time rate of disintegration is always negative. That's why we must place here negative sign, which indicates that as this time increases, this number decreases. That is why. Now this proportionality constant lambda, in physics we have given totally 4 names to that constant lambda. Remember, there are 2 names given in textbook. Other 2 names also we will see. Look, lambda is called radioactive constant or decay constant or disintegration constant or transformation constant. I repeat, lambda is called, look here, radioactive constant or decay constant or disintegration constant or transformation constant. Fine. Now let us see some points regarding value of lambda. About value of lambda, first point, value of lambda depends only on one thing, that is type of radioactive element. For different radioactive elements, value of lambda is different. For a given radioactive element, value of lambda is constant. It is time invariant. Time invariant means it does not change with time, correct? It simply depends only on type of radioactive element. Second thing, no external factor like pressure, temperature, electric field, magnetic field can produce any effect on value of lambda. Value of lambda remains unaffected by external factors like temperature, pressure, electric field, magnetic field. Got it? And third point, though you mix up given radioactive element with any other element chemically, then also there is no effect on the value of lambda. Value of lambda does not change though you are making any chemical mixing. Okay, fine. If value of lambda for a given radioactive element is more, then what will happen? If value of lambda is more, rate of disintegration will be more, and if disintegration takes place fast, naturally the life of that element will be short. That's why we call that element as a short-lived element. Short-lived element. Okay, fine. And if value of lambda is less, if value of lambda is very small, then this rate of disintegration also would be very small. Then disintegration will take place slowly. Then lifespan of that element would be very large, means it will have long life. That's why we call it long-lived. Just remember, if lambda is more, element is short-lived. Speak reverse. If lambda is less, element is long-lived. Simple. What is the physical meaning of lambda? What is physical interpretation of lambda? I am showing you. Take magnitude on both the sides. Then magnitude of dN by dt is equal to, when you take magnitude from minus, it will become plus. And now, if you take time interval dt, say 1 unit, then if dt is 1 unit, then put it here and then find out lambda. It will be dN upon n. Come on, dN upon n. Fine. What do you mean by dN? Number of disintegrations taking place in unit time. Correct? And divided by capital N, that is total number of possible disintegrations in that unit time. Correct? If disintegration is a successful event for you, then this numerator gives you number of successful trials and this denominator gives you total number of trials. In mathematics, the probability is defined this way. Number of successful trials divided by total number of trials. Such a ratio will give you probability of happening of a given event. Here given event means event of disintegration. If disintegration takes place, it is successful event or successful trial for you. Correct? So such a ratio will give you probability of disintegration of a nucleus, but don't forget in unit time. In unit time. Correct? So physical interpretation of radioactive constant lambda is that it gives us probability of disintegration of a nucleus of given radioactive element in unit time. Right? Fine. There are two units of activity which we will see in our syllabus. First is Becquerel, which is SI unit in the memory of scientist Mr. Henry Becquerel. Written this way, Becquerel, symbolized this way, capital B small q. The measurement is this. 1 Becquerel means 1 disintegration per second. 1 Becquerel means 1 disintegration per second. Correct? That is SI unit. Another unit is 1 Curie. Written this way, starting with small c, here starting with small b, and symbolized this way, capital C small I. 1 Curie is 3.7 into 10 to 10 disintegration per second. How would you define them? Very simple. Look, if one disintegration takes place in 1 second at a given instant of time in the given quantity of given radioactive element, then activity of that quantity of that radioactive element at that instant is said to be 1 Becquerel. I repeat, if one disintegration takes place in 1 second at a given instant of time in the given quantity of given radioactive element, then activity of that quantity of that radioactive element at that instant is said to be 1 Becquerel. Simple. Similarly, just tell me, can you define 1 Curie? 1 Curie. Can you define? Simple. 1 Curie is 3.7 into 10 to 10 disintegration per second. Come on. If 3.7 into 10 to 10 disintegration take place in 1 second at a given instant of time in the given quantity of given radioactive element, then activity of that quantity of that radioactive element at that instant is said to be 1 Curie. Simple? Fine. Wherever it is 1 disintegration per second, what you can write? 1 Becquerel. So here it is. You can just think of 1. 1 disintegration per second. 1 disintegration per second. If you replace it by Becquerel, then you will get relation between Curie and Becquerel. 1 Curie is 3.7 into 10 raised to 10 times Becquerel. 1 Curie is 3.7 into 10 raised to 10 times Becquerel. Okay, fine. Now, in practice, we also use some sub-multiples of Curie. Say 1 millicurie is 10 raised to minus 3 Curie. 1 microcurie is 10 raised to minus 6 Curie. Simple. Now, exponential law for radioactive disintegration. let us derive that law. Simple, huh? Derivation is quite simple. Recall this mathematical result. Just now we wrote dn upon dt equals to minus lambda n. dn upon dt equals to minus lambda n. Wait, take this n down, take this dt up. dn upon n equals to minus lambda into dt. Now take integration on both the sides. Integration 1 upon n dn, integration 1 upon n dn equals to minus lambda is constant, integration 1 dt, integration 1 dt, correct? But remember, here the variable is in terms of time. So here limits also must be specified in terms of time. Here variable is in terms of number, then limits also must be specified in terms of number. At time t equals 0, number of undisintegrated atoms is n0, and at time t, number of undisintegrated atoms is n. So here you should integrate this function between the limits 0 to t, and here you should integrate this function between the limits n0 and n. Simple. Now integration 1 upon n dn, it is nothing but natural logarithm of n. ln n means natural logarithm of n. Natural logarithm is that logarithm having base small e. Remember the value of small e? 2.718. Such a logarithm is called natural logarithm, symbolized this way, ln. And limits are from n0 to n, n0 to n. On right hand side, minus lambda is constant, integration 1 dt is t, from 0 to t, from 0 to t. But tell me, instead of n, now we should write upper limit, that is n only. After putting minus sign, instead of n, I should write n0. So natural log of n minus natural log of n0, and here minus lambda, instead of t we should write t, after putting minus sign, instead of t we should write 0. Now, if it is log a minus log b, what will you write next step? Log of a upon b. Similarly, natural log of n minus natural log of n0, it is natural log of this upon this, that is n upon n0. And here it is minus lambda into t. Fine. And now take anti-log on both the sides to the base e. When you take anti-log here, anti-log and log will cancel, giving you n upon n0. When you take anti-log here, if it is anti-log of x, it is e raised to x. Anti-log of y, e raised to y. Anti-log of this will be e raised to that. So anti-log of this means e raised to this, so it is e raised to minus lambda t, e raised to minus lambda t. Transfer this n0 here, n equals to n0 e raised to minus lambda t, n equals to n0 e raised to minus lambda t. Fine. This is the result in which on right hand side we have one function of time which is called exponential function because the base is e. Any function having base e, in English language we call it exponential function. We call it exponential function. So one such exponential function is involved here also in this result. That's why this result is known as exponential law for radioactive disintegration. N equals to n0 e raised to minus lambda t. Fine. Then you may have a question, what does it indicate? I am showing you. Take this down, so power will become plus, from minus it will become plus. Now n0 is constant, lambda is constant for given radioactive element, E is as such constant only. Now when time will pass, what will happen? T will increase, but as T increases, this whole ratio will decrease, that is value of n will decrease. T increases and decreases, T increases and decreases. Wait, when T is increasing, n is no doubt decreasing, but it is found to be decreasing exponentially. Then you may have a question, how is exponential decrement? I am showing you. Here is a graph of n versus t, that is number of undisintegrated atoms versus time lapse. Now tell me, that graph is like this, okay? Come on, tell me, At time t equal to 0, initial number is n0. Initial number is n0. Later on, what happens? As time passes on, this number goes on decreasing according to this curve. Fine. If that number is decreasing, then the element is said to be getting disintegrated, element is said to be decaying, because parent element is decaying. Parent element is decaying because the number is going on decreasing. Decrease means decaying. Because parent element is decaying according to this curve, we call this curve as decay curve for parent element. Decay curve for parent element. But don't forget, when parent atom disintegrates, it gets transformed into daughter atom. So as time passes on, no doubt quantity of number of parent atoms will go on decreasing, but on other side number of daughter atoms will go on increasing. The way this is exponential decrease for parent atom, same way you will get exponential increase for daughter atom. But then that graph, which is rising graph, will be called growth curve for daughter element. Growth curve for daughter element, not in your syllabus. In your syllabus, only this curve, which is called decay curve for parent element. Similarly, if you think for growth curve of daughter element, it would be like this. Correct? Fine. Don't allow this graph to touch this time axis, because if you allow this graph to touch this time axis, then on time axis this value will become 0. Tell me when n will become 0, provided time is taken infinite. Now you cannot show infinite time in the limit scale of the graph paper, so it is meaningless to show this graph touching to the time axis. Okay, leave it like this, incompleted. Okay, don't allow this graph to touch this time axis. Got it? Fine. This curve is called decay curve for parent element. Fine. How is this decrement? Initially value of n decreases quickly, later on slowly, further more slowly, further still more slowly, like that. As time passes on, rate of decrement goes on decreasing. Rate of decrement goes on decreasing. So as time passes on, it no doubt decays, it no doubt decreases, but it decreases slowly. Initially it decreases fast, then later on slowly, later on more slowly, later on more slowly, like that. Okay, fine. Just now we have obtained the exponential law for number, and the number law, that law, exponential law for number is this: n equals to n0 e raised to minus lambda t. But I is proportional to n. Look, this is nothing but I only. dn upon dt is nothing but I. So they replace this by I proportional to n. So when I is proportional to n, wherever it is n, you may write I. If it is here n0, you may write here I0. So now this will become exponential law for activity. This is exponential law for number. This is exponential law for activity. Now the mass of undisintegrated mass is proportional to undisintegrated number of atoms. So if m is proportional to n, then instead of n you may write m also. Instead of n you may write m. Instead of n0 you may write m0. Got it? So this is also now exponential law, but this is exponential law for number. This is exponential law for activity. This is exponential law for mass. Fine. What is m0? Mass of undisintegrated element at time t equal to 0. This is activity of undisintegrated element at time t equal to 0. This is number of undisintegrated atoms at time t equal to 0. Got it? Fine. Now let us define one more quantity called half-life of a given radioactive element, shown by symbol tau half. Fine. Consider this as a time scale. At time t equal to 0, number of undisintegrated atoms is suppose n0. Now we know one thing, as time passes on, this number goes on decreasing. So if this number is going on decreasing, at the end of certain time interval, this number will become half. So let it become n0 by 2. And for that, suppose this much time interval is required to get lapse. So at the end of this much time interval, it so happens that this number becomes half of initial number. Fine. Whatever time interval has been lapsed for making this number half of previous number, that same time interval itself is known as half-life, because number is getting reduced to half of initial number. Correct? Come on. It is shown by symbol tau half. We call it half-life. How would you define it? In a given radioactive element, the time interval at the end of which number of undisintegrated atoms becomes half of number of undisintegrated atoms before that time interval is called half-life of that radioactive element. I repeat, for a given radioactive element, the time interval at the end of which number of undisintegrated atoms becomes half of number of undisintegrated atoms before that time interval is called half-life of that radioactive element, shown by symbol tau half. Come on, recall exponential law which you have just now derived. N equals to n0 e raised to minus lambda t. N equals to n0 e raised to minus lambda t. Tell me, at the end of time equal to half-life, how much is the number? N equals to n0 by 2. N equals to n0 by 2. N0 as it is. E raised to minus lambda into t. T is how much? Tau half. T is tau half. Correct? You must put this both the values at a time. When you write time equal to half-life, number you must make half. So n equals to n0 by 2. n0 getting cancelled. 1 by 2 equals to, transfer this in the denominator, from minus it will become plus. Now take cross multiplication, come on. E raised to plus lambda into tau half will be equal to 2. Take log on both the sides to the base e. Come on, when you take log on both the sides to the base e, then you know when you take log here, this power will become multiplier. So lambda into tau half into natural log of e. Any logarithm to the base e is called natural logarithm. And when you take natural logarithm here, it is natural logarithm of 2. But this lambda into tau half as it is, natural log of e means log e base e, which is 1. And here base is e. You want to transform from base e to base 10? Yes, you can do that, provided you are multiplying with a factor 2.303. Base e to base 10, you must multiply by 2.303 into log of 2. In physics, when you write ln, base is e. In physics, when you write log, base is 10. It is to be understood. Okay? Lambda into tau half as it is, 2.303 as it is, log 2 to the base 10. From your log table, you will get the answer 0.3010. Now this into this comes out to be 0.693. And now find out tau half from here. It is 0.693 upon lambda. 0.693 upon lambda. 0.693 upon lambda. This becomes the formula for finding half-life of a given radioactive element. For different radioactive elements, value of lambda are different. So values of tau half is also different. And when we find out the half-lives for all the elements, we come to know that it ranges from very small time interval to very large time interval. It ranges from approximately 10 raised to minus 7 second to 10 raised to 10 year. Range of value of half-life for different radioactive elements is, remember, approximately 10 raised to minus 7 second to 10 raised to 10 year. Got it? One very important result let us derive. It will be useful to in the MCQs and in the numericals also. At time t equal to 0, number of undisintegrated atoms is suppose n0. Correct? If you allow time equal to half-life, then at the end of this much time, you know number will get reduced to half. So instead of n0, now it will become n0 by 2. n0 by 2 you can always write this way, n0 upon 2 raised to 1. Can you write? No problem? Fine. Now after this time, you allow another same time interval to get lapse. So tau half plus tau half will make 2 into tau half. But you know, whenever time interval is getting lapse equal to half-life, then number will get reduced to half of initial number. Before this time, what was the number? N0 by 2, correct? And now this number will get reduced to half of this will be N0 by 4. But this N0 by 4, can't you write this way? N0 upon 2 raised to 2, correct? Allow another half-life to get lapse. So 2 into tau half plus tau half, that is 3 into tau half. Again number will be reduced to half. This is the number before that time interval, and now this number is getting reduced to half. Half of this will be N0 upon 8. But can't you write N0 upon 8 like this? N0 upon 2 raised to 3. Can you write? No problem. Have you noticed one thing? Whatever is the power here for 2, same is the multiplier here. Here power is 1, then multiplier is 1. Power is 2, multiplier is 2. Power is 3, multiplier is 3. So in general, if power is n, then the multiplier also will be n. So for any radioactive element, remember, if you allow time interval to get lapse, which is equal to n times its half-life, then number of undisintegrated atoms reduces to 2 raised to nth part of initial number of undisintegrated atoms, correct? Or it will become 1 upon 2 raised to n times n0. Either you say n0 upon 2 raised to n, or you say 1 upon 2 raised to n into n0. Got it? Fine. Now let us see what is called average or mean lifetime. Average life or mean lifetime. It is to be shown by symbol tau. Very simple. Consider this as a time scale on which at time t equals 0, initial activity of given quantity of given radioactive element I am taking as I0. Now as time passes on, this activity also goes on decreasing exponentially. At the end of some time interval, it will so happen that this activity will be reduced to eth part of initial activity. That is, it will become 1 upon e times I0. That much time interval lapse itself is known as average life or mean life, shown by symbol tau. How would you define it? For a given radioactive element, the time interval at the end of which its activity becomes 1 upon e times its activity before that time interval is called its average life or its mean life, shown by symbol tau. I repeat, for a given radioactive element, comma, the time interval at the end of which its activity becomes 1 upon e times its activity before that time interval is called average life or mean life of that element, shown by symbol tau. Simple. I equals to I0 e raised to minus lambda t. This is nothing but exponential law for activities. Same law I have written here. But at the end of time equal to average life, tell me what is the value of I? I0 upon E. I equals to I0 upon E. This right hand side as it is. I0 will get cancelled. 1 upon E equals to, transfer this in the denominator, 1 upon e raised to plus lambda into tau. Now just take cross multiplication. E raised to lambda into tau will be equal to E, and then you can just match the powers because bases are same. Here also base is E, here also base is E, so powers should be equal. So lambda into tau should be equal to 1. If lambda into tau is 1, then what is tau? It is 1 upon lambda. Tau equals to 1 upon lambda. Tau equals to 1 upon lambda. How would you speak out this result in words? The average life or mean life of any radioactive element is always equal to reciprocal of its radioactive constant. Got it? Now let us obtain relation between tau and tau half. Very simple. tau half formula we have obtained just now, 0.693 upon lambda. So can you rewrite 0.693 into 1 upon lambda? Can you write? Fine. 0.693 as it is. But what is 1 upon lambda? 1 upon lambda is nothing but tau. So this 1 upon lambda can be replaced by tau. And now find out tau, transfer this. So 1 upon 0.693 into tau half. When you find out 1 upon this factor, you will get the answer 1.44 into tau half. So this gives you relation between average life and half life. But then you must notice this multiplier is greater than 1. So this is always greater than this. That's what I have written here. Tau is greater than tau half. For every radioactive element, its mean life or average life is definitely greater than its half life. Okay. Now the last point, what is called branch disintegration. There are certain radioactive elements in the given quantity of which both the disintegrations are taking place at a time. Some parent atoms emit alpha particles, they undergo alpha decay. Some other parent atoms, they emit beta particles, they undergo beta decay. So if both alpha as well as beta decay are going parallel at the same time, then we find practically that in that case the effective radioactive constant of such element is just equal to summation of radioactive constants of that element in case of only alpha emission and only beta emission. So this value of lambda is found to be equal to lambda alpha plus lambda beta, where lambda alpha is the radioactive constant of that element when it emits only alpha particle. This is the radioactive constant of that element when it emits only beta particle. Got it? Fine. But what is lambda from here? Lambda would be 1 upon tau. Lambda equals to 1 upon tau. So lambda equals to 1 upon tau. Lambda equals to 1 upon tau. Lambda equals to 1 upon tau. But the way I have written here lambda alpha, I am writing here tau alpha. The way I have written here lambda beta, I am writing tau beta. Simple. Again recall the same formula. Lambda equals to lambda alpha plus lambda beta. Now tell me, what is lambda from here? Lambda from here will be 0.693 upon tau half. 0.693 upon tau half. Lambda is 0.693 upon tau half. Lambda is 0.693 upon tau half. Lambda is 0.693 upon tau half. The way I have written here alpha, I am writing here also alpha. The way I have written here beta, I am writing here also beta. Now throughout the equation, what you can cancel? 0.693, 0.693, 0.6 getting cancelled. So what is left? 1 upon tau half, which is called effective half life. It is, come on, reciprocal of effective half life is just equal to 1 upon tau half in case of only alpha emission plus 1 upon tau half in case of only beta emission. Got it? Please remember both the results because we are going to use them in the numericals. Okay.